Hello there, we are going to be dealing with absolute value integrals. Now, first, before we actually deal with that, I actually want to go through an introduction on these absolute value integrals, right? So what I want to just go over quickly is absolute values in general. Let's just quickly look at their definitions and everything. So if I were to tell you that we want to find the absolute value of some number 3, right? This is equal to positive 3. So what happens if we were to put a negative number in? So if we say the absolute value of negative 10, well then this is just going to give us an answer of positive 10. So basically what happens is that the output will always be positive from what the inside of the absolute value was. So what if we were to define it? Let's consider some function f of x equal to x, right? So here we need to sketch the function. And let's see what this function looks like. It would look something like this, right? So it's the standard way it would look like is this, right? This is going to be your function. And you can see here it cuts the origin, and then it has a negative side and also a positive side, right? But if we were to look at the sketch of, let's say, f of x being equal to absolute value of x, we will note that, remember what I said? It will always have an output of positive, meaning remember that the output is working with the y values on the y-axis. Remember that we are working, if we choose some point over here to be x, this point over here, or let's actually choose a number, if we were to choose this to be, let's say, 2, this would be f of 2. Okay, so that would be our output, right? Now, what am I trying to imply over here? Whenever we have an absolute value of some function, every single negative y value, right? You can note how all of these y values are negative. All of the y values that are negative will immediately be converted to positive, meaning that all of this would look something like this. If you were to change the y values, okay? So it would look something like this. This is the absolute value of x. This one was already positive initially, so we didn't need to change it. Okay, cool. So it looks something like this. So let's look at our definition actually, and let's kind of verify some things. So here I'm gonna just divide this part, right? So we can like divide it into another section. Let's look at the absolute value of x, right? The absolute value of x is equal to, and here we can say it's defined by some piecewise, right, of where when x is positive, right, the output, remember this is the function x, right, x is the function in the absolute value. If x inside of the absolute value, or the function in the absolute value, is positive, so it's positive if x is greater, or equal to 0. And it will be negative if x is less than 0. So this is our standard definition. Some people would actually write it like this. They would say x equals to 0, right? Or they would say x if x equals to 0, something like that, right? But normally we would just include this over here. That's how we did it in university. So what we are trying to say is that we defined this initially, this function here, for when the x outputs were negative, it would have been less than 0, right? Where x is less than 0. So this area, this region right here, okay? And here, x would be positive when x is greater or equal to 0, this region over here, okay? And we can do this for any other function, even a quadratic or whatever, right? But what am I trying to imply over here? Well, before I can do that actually, let's bring a bound into this. Maybe that's probably like the best option right now. Okay, so what if we were to try and find the bound, let's say from, let's choose negative 2 to, let's say, positive 3, right? So we are going to say here, we are going to find the area, right, from negative 2 until positive 3. And how are we going to represent that? Well, when we are working with area, we are working with integration, right? So we are going to say area from x equals to negative 2 until positive 3 of what function we're working with. This is f of x equals to absolute value of x. So we're working with absolute value of x with respect to x, because we're working with the x-axis. Okay, so this is how we're going to write our function. But how are we going to actually integrate this? Well, first of all, let's look at our areas, right? We have an area here, right? And then it's cut over here by this origin. And then we have it continuing here. The area is just continuing. So what we are actually going to do is we are going to take a look at the positive version where it is, oh, actually I'm jumping the gun here, by the way. This, we wouldn't actually use reference from the absolute value graph. Funny enough, this is just a representation of what I'm trying to say. So let's just consider this one for now. And I'm going to show you what the normal x looks like. So we actually need to focus on this the most. Okay, so here, let's focus on that one. So it'll be the Cartesian plane over here. This will be y-axis, this will be x-axis, and then here, what we're going to do, we're going to draw the function of x equals to x, right? So the y equals x, like that. And now what we are going to consider, remember we're working with a bound. That's -2, and we are working with +3, okay? So something like this, and then all the way from here. And then what we are going to consider is the area between the x-axis and the function. That's normally what we deal with whenever we are working with the integral. In our case here, when we get into area between curves, you're going to see how it kind of differs a little bit. Instead of working with the x-axis, we're working with two different functions. But let's just focus on this one for now. Here, you can see that the area is under the x-axis. And what does that imply to us? If it is under the x-axis, then the y, the outputs, will be negative. And here, what do we notice? Here we have one side where the outputs are negative, right? So that's one part of the criteria. And then the other one here, we have another part of the interval. So it's actually from -2 until 0, the origin over here. And then from 0, so I'm going to quickly represent it here. From -2 until 0, we have negative x, right? Because x is, all the outputs are negative in that case here. And then here from 0 until 3, we can see it's positive, right? Which means it is going to be where the output will be positive. So therefore, we would use positive x over here. Okay. So now let's put that into an integral, right? Using this integral here. Okay. So what we are going to do is we are going to say that the integral, so I'm going to take this here, the integral over here, right, from -2 until 3 is equal to, and now we're going to just break it up. This is going to be equal to the integral from, let's start from -2 until 0, -2 until 0, because we're working with the negative side first. And if we're working with the negative side, that just means we are going to take the negative x with respect to x. Okay? And this is x equals 2. Don't worry, we'll do more examples if it's still a little confusing. And what are we doing actually? Remember, we're taking this area, right, this portion of the area, and we need to find the other area. So we just need to add this area in. So that's where the plus comes in. We need to add the other area, which is the integral from x equals to 0. Remember, we're starting from 0, and we're ending at +3. So it's from 0 until 3 of, and because the outputs are positive, it's above the x-axis, we are going to be working with the positive x values, meaning that we are going to be working with the positive function with respect to x. And now we can just integrate from here, right? Also, because it looks like the area is more over the x-axis, we should have a positive area in this case over here. Okay, so this is equal to, now we just need to integrate, right? So the integral of negative x is just going to be equal to negative, this should be x squared over 2. And then this is evaluated from x equals -2 until x equals to 0. And then what we are doing over here is we are just going to add, so let me just zoom out a little bit. We are going to add the other one, which is the x squared over 2, which is the integral of x with respect to x. And we're evaluating it from x equals to 0 until x equals to 3. Okay, cool. We need to continue, so let's just evaluate. Here, what do we notice? If we put in the x equals 0, right, then obviously we're going to get 0. If we plug 0 into this function here, this new function that we have, which is capital F of x, remember, because we integrated, we will get 0 because it's 0 divided by 2. So therefore we can really just disregard this one, and now we can plug this one in. So it's going to be -2, so it's going to be negative into -2 all squared divided by 2, and then we're going to have plus, and now we can work with this one over here, and then we're going to plug in the 3 into the new function, so it's going to be +3 all squared over 2. And do we consider the x equals 0? No, because once again it's going to give us 0 if we plug it into the new function. So we can disregard that. Okay, so now we can just add the areas together. So what we have is we have -4, so -2 all squared is equal to 4, so it's just -4 because the negative is outside, divided by 2, plus 3 squared, which is equal to 9. This is 9 over 2, and then what can we do here? We can just actually put these fractions together. We can write it as 9 minus 4, which is actually equal to 5 over 2. And can you see that the area is positive? I just predicted that. Why? Because our bound kind of shows that. We can see that the positive area is more than the negative area, and obviously that means we'll have a positive outcome. So that was just one example. So I'm going to do a couple more examples so we can kind of get used to how to do it. So obviously this time we are going to be dealing with more a little bit more challenging questions. We're going to do some quadratics. Okay, so the visual representation, sorry, my words, will still be there, don't worry. Okay, let's move on to the next example. All right, so let's say we were given the following absolute value integral. If we were given the integral from x equals to -1 until +4, and it's the absolute value of, let's do a quadratic, x squared minus 2x, because I feel like you guys, it's with the linear functions a bit too easy, right? So let's make it a little bit spicy over here. So from this point over here, we need to actually sketch the function first, so we can see at what point are we going to choose a negative and at which point we're going to choose the positive. Okay, so here we're going to do the following, right? We are going to actually sketch it, but before we can sketch it, we need to actually convert this to turning point form. And how are we going to do that? Let's complete the square. So what we are going to do is we are going to suppose that f of x equals to x squared minus 2x such that we have, now we can start with the solution here, f of x equals to, so we have x squared minus 2x. Now let's complete the square. How do we do that? Well, let's recall, we're going to group the first two terms. We obviously don't have a c value here, so we're just going to say it's 0, but we don't have to write that down. And what we're going to do here is we're going to take the function of x, and we are going to take the inside of the bracket over here, minus 2x, and then we're going to have plus, it's going to be b divided by 2, which is -2 over 2, all squared, close the bracket, and we're going to minus it by, and the same thing, -2 over 2, all squared. Note that we're manipulating it so that these eventually cancel, they're equal to 0, but we did manipulate the expression. Okay, so that it still holds true. And then what we can do, we can simplify. We can say that this is x squared minus 2x, and then we have -2 over 2, which is equal to -1, -1 all squared, which is equal to +1, so it's +1. Okay, and minus, and it's going to be +1 again, so it's -1. Okay. So from here, we have the function of x, right? So therefore, the function of x is equal to, and if we factorize this, we're actually going to get the following, right? We can see it as factors of x, and 1 and 1. And we know that 1 and 1 can give us -2, or just 2, right? So this is how we're going to do it. The 1 gets a negative, so it's going to be x minus 1, and the negative and a negative, so we see from here, x, negative and a negative gives a negative, sorry, a negative and a positive gives a negative, and this is 1. Minus 1. Okay, so we just factorize that. And then from here we can see we can rewrite this as x minus 1 all squared minus 1. Okay. We just completed the square and we put it in turning point form, where we have the a value being equal to 1 and our p value, which is -1. And our q value, which is equal to -1. So we can just sketch it as follows. In order for us to sketch it, we'll see it as the following. It will be like this, not like that, but like this. Okay, so it'll be like this, and then we can sketch it. We can see that our turning point is actually going to be here. Our turning point, we're going to use, it's going to be x equals 2. We're going to change the sign over here, right? Or we can just find it by saying x minus 1 equals to 0. We're taking the bracket and we're letting it equal to 0, such that x is equal to positive 1, meaning it's going to be at x equals positive 1. And the y turning point will be just that value outside, which is negative 1. Here, let's sketch the function. We'll have the turning point at 1 and negative 1, which we can situate somewhere here. Okay. So this will be 1 and negative 1. Like so. And then what we have here is we need to look for the intercepts. And how do we find the intercepts? Well, we just have to take the function and we need to factorize it from there. It's actually easily factorizable. Like we can actually factorize it. So let's do the following. F of x equals 2, we had x squared minus 2x, right? And we can actually just take out x as a common factor, such that x into x minus 2. And then remember, we want to find the x-intercepts, right? So x-intercepts implies that to us that we need to let y equal to 0. Because on the x-axis, y is equal to 0, right? This we call our y equals 0 line. And this is our x equals 0 line. Okay. And that means we're going to let this be equal to 0. Our outputs. And now we can say that therefore, we have this bracket, which is x is equal to 0, or x is equal to, or x minus 2 equals to 0, such that x will be equal to positive 2. Okay. So we have x equals to 0 and x equals to 2 from this point over here. And now we can actually sketch or we can plot the x-intercepts. So 1 will be here, so let's say that 2 is going to be somewhere here. And then 0 is obviously somewhere here. So we have something like this. So the function will look something like this and like this. So let's just suppose that the point is actually here. This would be 2 and this would be 0. Okay. Cool. Now we need to look at our bound, which is negative 1 until positive 4. Okay, this is a funny part. Let's just extend this part over here because I did not expect that. So it looks something like this. And then let's say 4 is somewhere over here, right? Let's say that 4 is somewhere here. So let me make it a little bit neater. So the point 4 lies right here, and the point negative 1 lies somewhere here. Okay. So what we are actually going to do is we need to consider all of the area between the x-axis and the function. So if we were to look at the first part, so let's look from left to right, we will notice that from negative 1, we'll see there's area here, right? Between the x-axis and the function of f. So this is f. And then watch how it actually goes under the x-axis here, between the x-axis and the function. Okay. And then from here, we can see it immediately goes back to positive. Okay. So that's pretty cool. So what do we notice over here? What we notice is that it is going to be positive. So the function is actually just going to be positive, right? Over here. Then the function here will be negative because it's below the x-axis. And here, the function will be positive because it is above the x-axis. This area is above the x-axis. So basically, we're just going to add all these areas together with respect to the intervals. So it's going to be positive from negative 1 until 0. Then it's going to be negative from 0 until 2. And then it's going to be positive from 2 until 4. So let's do that. Okay. So I'm going to take this sketch actually. And I'm going to move it. So we're going to move it nicely over here. Right, just slowly and gently, so no worries at all. Ah, there we go. Cool. Cool stuff, eh? Technology. All right, cool. From here, now we can do the integral, right? Remember, we were looking for the integral from x equals to negative 1 until 4 of the absolute value of x squared minus 2x with respect to x. And we can rewrite this as the following. So we can say it's equal to the integral from x equals 2. So let's look at the interval from -1 until 0, right? It's going to be from -1 until 0. It's going to be positive. The function in the absolute value here, because remember that's represented as f of x, is going to be positive. So we're going to choose positive x squared minus 2x. Put that in brackets with respect to x. And now we're going to add the other area between 0 and positive 2. Okay, and that is the negative area. So we can say the integral from x equals to 0 until positive 2 of the negative 4x squared minus 2x dx. Okay, and then we're just going to add the other area from x equals to 2 until 4. 4 is the last part over here, and note how they're going to be positive. So it's x squared minus 2x with respect to x. It's positive because it's above the x-axis. So note the pattern that we have right here. It's really not that bad. Okay, so from here, we can say this is equal to, so let me continue it here. It's going to be equal to, we're just going to integrate all of this, right? So we're going to have, should be x, so we're going to integrate it. It's going to be x squared, so that's going to be x cubed over 3 minus, and then we're going to have 2 multiplied by the integral of x, which is x squared over 2. Okay, and this is evaluated at x equals to -1. Let me just move it a little bit upwards so we can see the other intervals. There we go. So it's going to be from -1 until 0. And then we're going to add it with the one which was negative, or we can actually just take the negative out and it gives us a minus, right? So we can actually take the negative outside of the integral. And then we have the we basically have the same thing. So we're going to have x cubed over 3 minus 2 into x squared over 2, evaluated at x equals to 0 until x equals to 2. And then we're going to have plus, and then we're going to have the same thing, x cubed over 3 minus 2 into x squared over 2, evaluated at x equals to 2 until x equals to 4. Okay, and now we can evaluate that. Here, what do we notice? If we plug in the 0, right, we will obviously get 0 as an outcome, because 0 divided by a number is 0, and 0 divided by another number is just equal to 0, so we can disregard this. -1, let's do that. So with -1, we can plug it in, so we are going to have -1 all cubed divided by 3, so let's put a bracket here for the first one, and then these 2's can actually cancel out. So these 2's can cancel out, these 2's can cancel, and these 2's can also cancel. Okay, so here we are going to have minus, and it's going to be -1 all squared, and then we're going to have this should be minus as well because of the sign outside. Now we're going to evaluate this, right? So we're going to take this 2 and we're going to put it into evaluated with the new function. And then we're going to have the following. It's going to be 2 all cubed divided by 3 minus 2 all squared. Okay. And with the x equals 0, remember we can disregard that because it's going to just give us 0. For here, and I also just remembered something, by the way. With the negative, and this is actually, now that I look at it, I don't even recommend doing that. When we're looking at x equals to 0 first, what I normally would say is you can disregard it, but I just remembered there should be a negative as well. There should be a negative somewhere outside over here, right? Somewhere outside here, because remember, this is actually our capital F of it should be B. No, this is our capital F of A, right? And it came from the minusing of capital F of B, right? But we disregarded capital F of B. So therefore we left with negative F of A. And that's why this negative should actually be here. So if I did do it in the previous example, I do apologize. I'm probably going to state it there in the comment section. So before you comment like, oh, Dylan, you left it out. I mean, like, now I realize it. It's just math. Anyway, cool. So from here, now we don't have to deal with the zeros, so that's cool. But you have to deal with calculations, so I'm just going to get the answer out. But first of all, hold on, relax. We need to evaluate. So here we're going to add it by, and we're going to just take in the 4. So it's going to be 4 all cubed divided by 3 minus 4 all squared. And then we're just going to minus it by, so we're going to take that and we're going to actually minus it by, so I'm going to actually write it somewhere here, minus, and then we have, let me just use a square bracket in this case here, minus, and then we're going to have the other one evaluated at 2. So here it's going to be 2 all cubed, so 2 all cubed divided by 3 minus 2 all squared. And now we can close that bracket. Okay, we're just minusing the whole function here. So that's why I put the negative there and the brackets. Cool! If we evaluate all of this stuff, and if we put it on a calculator, or if you just like do the steps, you will get some answer, which is 28 divided by 3. So this would actually be the area, and let's kind of see that, right? Let's see that on the function. Would that be true? Now, if we were to look at the area, right, you can see that from 0 to 2 until 0 to 4, this should actually be 4. I don't know why this is a 1. This is equal to 4, sorry. Here, from 2 to 4, it's just like, it's about the same as from 0 to 2, right? Because it's also 2 intervals in the x-axis, but we have an extra 1 interval here. So that means that this answer should be positive. The positive overtakes the negative, so therefore our answer here would be positive. Okay. And I think actually now that I look at it, this is basically all you do with absolute value of integrals, right? Here's a summary of what we actually do. We have to obviously sketch the normal function first. So as you can see, we start off with the absolute value, but we need to suppose that f of x is equal to the original function without the absolute value. And then what do we do afterwards? Well, I mean, if you're doing a quadratic, complete the square, but the main goal is to sketch the function, right, on a Cartesian plane. Find all the x-intercepts because that's important. And then once you find the x-intercepts, you can use those intervals with respect to your bound for the integral, whatever you find in the area for, and you can just add all those areas together, right? One will be positive, the other will be negative, and then and so on and so on. Okay, so that's basically what we're dealing with when it comes to absolute value integrals.